Hey, welcome to video 4 circuit components. Starting off this video, let's talk about wires. Generally, when you see wires, you'll see them being stranded, braided wires instead of one solid piece of copper. The reason why they do this is because stranded copper wires are more flexible and they actually have reduced amount of resistance. This is because electrons like to flow on the outer surface of copper, not directly through the center of copper. Wiring is measured in AWG, which stands for American Wire Gauge. The weird thing about American Wire Gauge is it measures the diameter of the copper, so the outer surface, the outer circle of the wire, but it does not include the sheathing. It does not include the outer insulating sheathing. And the weird thing about all wire gauge numbers is the smaller the number, the larger the wire. It doesn't really make sense the way they do it. That's just the way they do it. So now when it comes to ISO metric wiring, it measures a cross-sectional area, as you see in the red. This is the cross-sectional area. And it's measured in millimeters squared. The larger the metric number, the larger the diameter. So ISO makes sense. The larger the number, the larger the wire. American wire gauge is the exact opposite, where it's the larger number is actually a smaller wire. You can see it on the chart here. If we have a 0.5 ISO measurement, which is a 20 gauge American wire gauge size, we have a 4 amp capacity through that wire. Depending on the amount of amperage you want a bigger wire. Now, if we have a 30 amp capacity, or if we want a 30 amp capacity, we're going to go with an all wire gauge of 10 and a metric size of 4.0. Now, the weird thing about American wire gauge is when they came up with it, they didn't really think past going past a all wire gauge of 0. So they have what's called aughts. So once you go past all wire gauge of 0, you go to an all wire gauge of 2-aught, all wire gauge of 3-aught, an all wire gauge of 4-aught. It doesn't really make sense, but they ran out of numbers, so that's how they do it. Sometimes it's just summarized as 4-0 or 3-0 or 2-0. Kind of a weird way of doing it. Another thing to note about wires, they have what's called a tracer on a lot of wires. So when you see certain engine harnesses or chassis harnesses, they'll have what's called a tracer. And this is just an identifier. So they'll say it's a blue wire with a red tracer. And it identifies it because you could have multiple blue wires in a harness, multiple red wires in a harness. It just makes it a lot easier. Now, when it comes to switches, for descriptions for switches, we have two different styles. We have a normally open or a normally closed switch. What that means is if you leave it alone and touch nothing with it, a normally open switch would be an open circuit. And a normally closed switch would be a normally closed circuit. Once you activate that switch, for example, if these are buttons, if you push a normally open switch, it'll become closed. If you push a normally closed switch, it'll become open. They also have identifiers for poles and throws. Poles is the number of inputs, and throws is the number of positions that can be used to complete a circuit. That means that although this is an open circuit, this is not considered a position. The only position you can have is straight down as when it's making contact. So this would be a single pole, single throw. That's how they're identified as SPST for this one here, because it's making contact and has a circuit when nothing's being applied. This would be a single pole because there's only one input, double throw. You see here, there's a bridge connecting the two inputs, but it has two inputs. So it's double pole, single throw. See, now it's a single throw because when it's open, it's not making contact, but because they're connected, although they have two circuits, they're only activated at the same time on the same position of that switch. As far as fixed resistors go, fixed resistors is kind of interesting. They have identifier bands most of the time. The identifier bands indicate the amount of resistance that resistor has. So, for example, if you look at this chart here, we have a brown strip for our first number. Now, generally speaking, I like to work my way back to front. So, because there can be more than four numbers, there could be five numbers, six numbers, seven numbers, or seven bands. They can basically be infinite to determine what kind of resistance you're having, what kind of tolerance you're having. I wrote temperature coefficient for this one here. Most resistors don't have this temperature coefficient band, but some of them do. So keep that in mind. But if you look here, our first band, we have a numerical value. Our second band, we have a numerical value. And those are just number places. So if we look at brown, brown's a 1, and that would give us the first letter of 16. We look at blue, it's a 6. That would give us a second number of 16. So yes, our number is going to be 16 that we start off with. We look at our third color is yellow. So you see yellow is 10 to the power of 4, which means we take our 16 here, times it by 10 to the power of 4. In case you don't know how exponents work, when we have 10 to the power of 4, we're timesing 10 4 times. So we're adding 4 zeros to 16. When we add 4 zeros to 16, we have 160,000 ohms of resistance, or 160k ohms. We look at this band here, this number 4 band. We can see number 4 band is the tolerance band. It's written as a plus or minus percentage, and that's how much allowed deviation that resistor can have. So if it's this gold color, it can have a plus or minus 5% deviation, which I wrote down here as a plus or minus 5% deviation. Let's talk about potentiometers. Potentiometer is a variable resistor. It's got 3 wires that go to it. This is the symbolic drawing potentiometer. And you have a input, which is probably 5 volts or source voltage. I'd say most likely you'd see source voltage. And then you would have a ground. And this is a resistor. So just imagine this is one big resistor. And you have this rod that connects on this resistor plate. As you turn that, it varies the amount of resistance and it puts a different amount of voltage through here. If you remember how a circuit works, is we have voltage drops in our circuit. Let's say this is just our gauge. We have 12 volts here, and we have a 2 ohm resistor at, let's say this is 2 0.2 amps. So we take 2 multiplied by 0.2 amps, give us 0.4 volt drop. So we have a 0.4 volt drop. We would have 11.6 volts coming on this side going to our gauge, which will be, let's say that's full. I would read maximum on our, let's say, fuel. And that's how exactly a fuel sending unit works. So inside your fuel tank, you'll have a little float here that basically floats to the top of the level. And as that goes up or down, it goes across a potentiometer inside the bottom. That potentiometer sends a voltage, 3 wires there. It sends a voltage back to your fuel gauge, to your ECM, to something, and that's how it reads how much fuel you have in your tank. Talk about circuit protection devices. We got different styles of circuit protection devices. I'm just going to talk about fuses and circuit breakers. Starting off, this is the circuit drawing for a fuse. And we got different styles of fuse. We have these Like, this is the type of fuse you'd see inside a multimeter, these glass tube fuses. And then you got these style of fuses. There's three different sizes for them. They have mini fuses, auto fuses, and maxi fuses. And they're color coded as far as the amount of amperage they can handle. And the way they work is there's just a small amount of material here, and once that heats up to a certain level, it breaks or blows. That's what protects your circuit. So that's going to be the first thing that blows on your circuit is your fuse, which is designed to be a replaceable device. For mini fuses, you have different color codings for amperage rating. You can see tan is 5 amps, yellow is 20 amps, green is 30 amps. They try to keep it pretty consistent. Auto fuses use different colors. There's more auto fuses. You got violet being 3 amps, and then you got green being 30 amps, again, same as the mini fuse, and then yellow being 20 amps, same as the mini fuse. Blue, same as the mini fuse, 15 amps. When you get to maxi fuses, they kind of change it up a little bit. Yellow and green, still the same. Now they use amber, red, blue, brown, and what's called a natural color. When you see natural color on both of these, it just means that the outer shell is totally clear. And then once you get past this 80 amps for a maxi fuse, you get mega fuses, which they all look the same. They don't really have an identifier except for the number stamped on them. This is a 100 amp mega fuse. It's basically just a piece of copper that's burns out. When we get to circuit breakers, this is the circuit drawing for a circuit breaker. They have a few different styles of circuit breakers. They have resettable circuit breakers and they have auto reset circuit breakers. So a lot of times you have to manually reset a circuit breaker or re-push the contact back in, and it's like spring loaded so that once it heats up enough, it separates that metal and it only goes back once you reset it. When it has these, once you get this metal hot, it expands, and once it expands, it opens that contact. Once it cools off enough, closes the contact back up and allows current to flow again.